Okay, so hello everyone. Welcome to our seminar this week. So the speaker today is Professor Christiane Tammer from Martin Luther University Halle-Wittenberg. Christiane is also a professor in Institute of Mathematics and also an editor-in-chief of Optimization Journal. So everyone here probably know Christiane very well, because he's an expert in vector optimizations. And also she's a very supportive member of our optimization community. So I know that Christiane was in Australia before, but haven't been to Perth. So welcome to Perth. So now, thank you very much for agreeing to give a talk in our seminars. So now the stage is yours.
Yeah, thank you very much, Hoa. At first, hello to everyone here, and many thanks for the kind invitation to give a talk in your seminar. It is a great pleasure for me to meet you and Alex, Vera, and the others in this way. Is it possible for you to see and hear me? Is everything okay? Yes. Okay. Yeah. In my talk, I will speak about subdifferentials and Lipschitz properties of translation invariant functionals and several applications. This is a joint work together with Bao Truong from the Northern Michigan University. Yeah, the aim of this talk is to study problems without convexity assumptions. And especially in vector optimization, Z optimization, but also for separation theorems, one needs certain tools to handle such problems without convexity. And for doing this, I will introduce a scalarization approach or separation approach by translation invariant functions. Yeah, in order to show necessary optimality conditions in optimization without convexity assumptions, one needs certain concepts of generalized differentiation. And this is the second part of my talk. Furthermore, in order to derive such optimality conditions, we need the structure of the subdifferential of the scalarizing functionals. And then we can use calculus rules from generalized differentiation in order to show applications in Z-valued optimization. At the end of my talk, I will speak about some applications in approximation theory, and I will give some conclusions. Yeah, at first, I will describe the framework. We will deal with real linear topological spaces for some properties. Of course, we don't need a topology. However, for deriving the optimality conditions to have concepts of generalized differentiation, we need a topology, and we will speak about aspirant spaces, especially later on. Yeah. Sometimes we suppose that a subset of this linear topological space is solid. This means that the interior of A is non-empty. A subset is proper if it is not equal to the empty set and not equal to the whole space. The pointedness of ZA is described by this inclusion here. And as well known, of course, a Z is called a cone if this property here is fulfilled, and a convex cone if it is a cone, and we have additionally the assertion that A plus A is equal to A. We will call a proper cone non-trivial. Here you can see the well-known definition of the dual cone. to a cone Z in a linear topological space. This is a well-known definition. Yeah, for deriving the structure of the subdifferential of the scalarizing functional, we use sometimes the recession cone to a ZA. This is a well-known definition of the recession cone. And furthermore, we will use the barrier cone of A, denoted by bar A, and the barrier cone is nothing else than the domain of the support function of the ZA. So in order to formulate optimization problems in a very general sense, we introduce the domination set, theta, here, and we suppose it is proper and 0 belongs to the closure of theta. And using the relation with respect to theta, denoted in this way, here we can introduce a pre-order. Yeah, we say y1 is smaller or 2 minus theta. Yeah, as you know, if theta is equal to Z and Z is a non-trivial closed convex and pointed cone, then we introduce with 1 a partial order in Y. However, we will not suppose the convexity and the conical property with respect to the domination set theta. Yeah, and using this domination set theta here, we can define now theta minimal points of a certain set sigma, this is sigma, as a subset of Y, and Y bar is such a theta minimal point if the intersection of sigma and Y bar minus theta contains only the single element Y bar. This means that for each element belonging to sigma, this relation implies that Y is equal to Y bar. This will be our solution concept when we are dealing with Z optimization or vector optimization problems. So, and a main tool for dealing with such vector or a Z optimization problem is a scalarization technique. We introduce at first scalarization directions of a Z. Again, we consider a ZA here, a proper set. Here we don't need topological properties for Y, so we can say a linear space Y. And an element K not equal to 0 is called a scalarization direction of A if A does not contain lines parallel to K and the scalarization conditions, this one, is fulfilled. Here the ZA and also the direction K are involved. And with this assumption here, that A does not contain lines parallel to K, we get that this scalarizing function is greater than minus infinity. And furthermore, with this condition, we get the well-definedness of the scalarizing functional. Yeah, we will denote the set of all scalarizing directions by this symbol here. And now we can introduce nonlinear scalarization functionals or nonlinear separation functionals, or later we will say translation invariant functionals, because this is one of the most important properties of this functional. Again, we consider a subset of Y and a scalarization direction K here. And then because of this assumption here, the function is greater than minus infinity, such that we have a function from Y to R in union with plus infinity. And this is the definition of this convention. This functional is called nonlinear scalarization functional with respect to the ZA involved in the definition and with respect to scalarization direction K that you can see here. Yeah, and this is our main definition here for our approaches. So, and here I will recall the most important properties of this scalarizing functional. We derived these results here in a joint paper with Alfred Göpfert and Konstantin Salinescu. Furthermore, in our book from 2003, together with Alfred Göpfert, Hasan Riai, and Konstantin Salinescu, in this theorem we have shown these results here. Very important is the lower semi-continuity of the scalarizing functional on its domain. And for geometrical interpretation and many assertions, this level Z property of the scalarizing functional is very useful. We consider this level Z with respect to the level tau here, and this is exactly the Z on the right-hand side of the scalarizing functional with tau instead of t. So, yeah, this is a level Z property, and then the translation invariance along the scalarization direction K. This is this property here that for all elements y and for all t, we have the objective function values at y plus tk are equal to the objective function values at y plus t. So, and this property is called translation invariant property. And in our papers, we have shown that the scalarizing functional has this property. However, it is interesting that Jaschke and Küchler in 2001 have shown that each translation invariant functional has the representation phi ak. So, and in order to have some differentiability properties, we are looking also for the convexity property of the scalarizing functional. The functional is convex if and only if the shifted ZA in the definition of the functional is convex and positively homogeneous if and only if A is a cone. So, and these properties will be used later on, and for deriving so many results, these properties are important. In the theorem, we suppose the closedness of A. However, it is possible to relax the closeness of A using the vector closure of A in the direction K. The vector closure of A is defined here. This is this definition. And it is easy to see that phi with respect to A and K coincides with phi with respect to the vector closure of A and K. So, and of course, if A is a closed set, then we have this property. This is clear. A is equal to the closure of A and equal to the vector closure in the direction K of A. However, the converse assertion does not hold, as you can see in this example. If we choose A in this way here, and the direction K is given here, then it is easy to see that A coincides with the vector closure with respect to K of A. However, the closure of A is equal to A in union with the set, and this means that A and closure of A does not coincide. Yeah, this is a short discussion of the closeness of the shifted set A in the definition of the functional. Yeah, here you can see an illustration of the functional phi ak. If we choose k equal to k0, this is this vector here, and A equal to K here, and this is a natural ordering cone in the two-dimensional space. Then we have this vector K0, K equal to K0. This is this one. Then we consider TK 0. This is this line here. And furthermore, we can describe the right-hand side of the restrictions in the functional. Here, this is TK0 minus K. You can see it in red color. This is a shifted Z K here in the direction K0. So, however, in the definition of the function, we have this infimum over T belonging to R. And taking into account this definition, we can see here in this illustration that the objective function values of y bar and y hat coincide. This is equal to t bar. We have the same objective function values. And here is the infimum over t. If we would choose larger t, then we could find an element t belonging to R that is smaller as t bar. And if we would choose a smaller t here, then of course y bar and y hat doesn't belong to the set here, such that as a restriction is not fulfilled. So this was a short illustration. And here it is interesting to mention that Krasnodębski and Rubinov were using such a construction in the context of operator theory. Yeah, in order to prove separation theorems for not necessarily convex sets, we introduce this functional as separation functional, or in vector optimization as scalarization functional. These are the first papers here, and I like also to mention a joint paper with Emil Ivanov, published in German language. Furthermore, the properties that I already mentioned are described in the paper together with Alfred Göpfert and Konstantin Zainescu. And here it is also interesting to mention that Pascoletti-Serafini introduced an optimization problem that is related to the scalarizing functional phi ak for a special case in finite dimensional spaces and so on. However, they did not introduce a functional. They introduced an optimization problem. And the properties of this functional were shown in these papers and many other papers on this field. Furthermore, there are interesting applications in economics. Lüneberger especially introduced the so-called shortage function with respect to the production possibility set, y here. And here we have a reference vector g. And here you can see that this shortage function discussed by Lüneberger is nothing else than our functional phi a k with g instead of k and y instead of a. Another function introduced by Lüneberger in production theory was the so-called benefit function. Yeah, in several papers together with Elisabeth Köbes, we discussed concepts of robustness in optimization under uncertainty. Here I mentioned one paper together with Katrin Klamroth, Elisabeth Köbes, and Anita Schöwe, published in ICHOR. And here we have shown that many known concepts of robustness can be unified using the nonlinear scalarizing functional phi ak. And furthermore, it is possible to derive new concepts of robustness using this nonlinear scalarizing functional. Yeah, in mathematical finance, coherent risk measures are well known, and especially in the paper by Arzner and co-authors, and in many other papers, such coherent risk measures were discussed, and already Arzner has shown that a coherent risk measure can be described by the nonlinear scalarizing functional phi ak. And there is another interesting link to functional analysis. In not only one, but here I mentioned one paper by Rubinoff and Singer. They discussed topical functions. And topical functions are monotone functions that are translation invariant. And so we have the relationship to our nonlinear scalarizing functional phi ak. So in order to discuss the subdifferential of the scalarizing functional, I would like to recall the results from the literature that we derived several years ago. This is a joint paper together with Marius Durea from 2009. Here we derived the structure of the subdifferential of the scalarizing functional for the case that the shifted ZA is equal to C, and C is a non-trivial closed, solid, and convex cone. And K belongs to the interior of C. Of course, these are very strong assumptions. However, under these assumptions, it was possible to derive the first results. At first, following from our more general results, the functional phi ck is a continuous sublinear monotone with respect to the interior of C and translation invariant along the direction K. And here you can see the structure of the subdifferential of this scalarizing functional. Here we have elements belonging to the dual space, belonging to the dual cone to C. This was C here, with these properties. And for deriving this result, we were using important assertions by Rubinoff. Yeah, and if y bar is equal to 0, then the subdifferential has a very nice structure. The subdifferential can be described by the intersection of the dual cone to C and this hyperplane depending from the scalarizing direction K, and this hyperplane is derived here. Yeah, here the vector K is involved. Yeah, this was shown under very strong assumptions, and as you know, in general spaces, many natural ordering cones does not or do not have the property of a non-empty interior. So, and in order to derive some more general results, also in the joint paper with Marius Durea, we have shown if the shifted set A is a non-trivial closed and convex set, and K is a scalarization direction of A, then the subdifferential of the scalarizing functional at y bar has this structure here. This is an element of y star. It was not possible for us to show that y star belongs to a certain dual set or something like this, like in lemma 5. However, we have these properties here for the subdifferential. 1 year later, we published a paper together with Constantin Salinescu, and here we computed the subdifferential of the scalarizing functional under more general assumptions. We suppose that A is a non-trivial closed and convex set with a free disposal property. What is the free disposal property? The free disposal property is a property that for the set A and a certain closed convex cone C, it holds that A plus C is equal to A. This is a well-known property in production theory. And for us, it was also important for mathematical results to have this property. And furthermore, we suppose that K doesn't belong to the negative recession cone of A. Then it was possible to compute the subdifferential of the scalarizing functional. Yeah, here in difference to this result, we have that y star belongs to the barrier cone of A. This means to the domain of the support function to A. And here we have the same properties like in lemma 5 for elements belonging to the subdifferential. Yeah, these are our formal results. And now we were trying to relax the convexity assumptions concerning A. This means that we will study the case that the shifted ZA is non-convex. And for deriving corresponding results, we cannot use the Fenchel subdifferential of convex analysis. And so we were looking for concepts of limiting generalized differentiation. Yeah, especially in the group of Alex Kruger, these notions are well known because he derived it together with Boris Monotonicity. And so I like to recall these notions. The regular normal cone is defined here, denoted by n hat, with respect to a subset omega in an Asplund space. So, and the limiting normal cone is defined here. Here we are using the regular Frechet normal cone, this is this one, and the Penlevel-Kuratowski outer limit. So this is the limiting normal cone. And using the regular normal cone and the limiting normal cone, we introduce the regular coderivative for z-valued map, capital F. And we consider elements x bar, y bar belonging to the graph of F. The regular coderivative is defined here using the regular normal cone, and the normal limiting coderivative is defined here using the limiting normal cone. So, and here we have the weak star convergence in each component x star, y star. And we will introduce another concept, the mixed limiting normal cone and the mixed limiting coderivative, where we replace the weak star convergence in the second component by the norm convergence in the second component. This is this one, the mixed Monotonicity limiting coderivative here. And as you can see here, we keep the weak star convergence with respect to the first component, but we replace the weak star convergence in the second argument by the norm convergence. And details of these coderivatives are presented in the books by Boris Monotonicity. This is volume 1 and 2 from 2006, and this is a recent book. So, yeah, because of the natural lack of compactness in general spaces, and in order to have some calculus rules in such a general framework, we have to introduce certain assumptions that a subset of an Asplund space is sequentially normally compact. This is the PSNC property. Yeah, we consider an element y bar, x bar, y bar belonging to omega, and suppose that omega is locally closed around this point. And then we are speaking about the PSNC property of omega if for all elements described in 7, we have this implication here with the weak star convergence and the norm convergence. Yeah, of course, it would be interesting to ask for sufficient conditions for this PSNC property, and as well known, convexity assumptions in the interior of omega is non-empty are sufficient conditions. So in order to derive the structure of the subdifferential of z-valued mappings, we introduce the notion of the epigraph of a z-valued map F with respect to the domination z theta. This is a definition of the epigraph of F where the domination z theta is involved. Furthermore, we will use in the definition of the subdifferential of a z-valued map the epigraphical multifunction of F with respect to theta. This is this definition here. And yeah, of course, we have this property that the graph of the epigraphical multifunction coincides with the epigraph of F. So, and now using this notion of the epigraphical multifunction, we introduce the definitions of several subdifferentials of z-valued mappings. F is a z-valued mapping, theta the domination z. And we have here some closeness assumptions concerning the epigraph of F. And here we have the regular subdifferential, where we are using the regular coderivative of the epigraphical z-valued mapping with respect to F. The basic subdifferential is defined using the normal limiting coderivative of the epigraphical multi-valued functions or z-valued map F. And furthermore, we introduce the singular subdifferential using the mixed limiting coderivative of the epigraphical map with respect to F. These are three subdifferentials useful for z-valued mappings. So we will deal here with z-valued mappings, and if we are looking for the subdifferential of the scalarizing functional, we will consider the epigraph of this scalarizing functional. So these are the first results now. We are looking for the subdifferential of the translation invariant functional phi ak. We suppose that Y is an aspirant space and A is proper and closed. We consider a scalarization direction K and our translation invariant functional. And then we get, for both cases, for the regular subdifferential and the limiting subdifferential of the scalarizing functional, at an element y bar, t bar belong to the epigraph of the scalarizing functional, and for lambda belonging to R, that the subdifferential has this structure here. Yeah, here we are using such hyperplanes for lambda belonging to R. This is this one. And we have this lambda because we are dealing with elements belonging to the epigraph of the scalarizing functional. And then we have the intersection with respect to the negative normal cone. Here we have the regular normal cone as well as the limiting normal cone at this point with respect to A. This is the first result, and I would like to show you the sketch of the proof. Yeah, here we introduce a z-valued map because we have our notions for z-valued maps F, and F of t is here the right-hand side in the restriction of the scalarizing functional. Here we have the shifted ZA and scalarization direction K. So, and using this z-valued map F, it is possible to show using lemma 3, this was a lemma with the properties of the scalarizing functional, lower semi-continuous level, that property, yeah, translation invariants that are important here. And then we can show that the graph of the inverse of this z-valued mapping coincides with the epigraph of the scalarizing functional. And then we can apply coderivative sum rules especially in the book by Boris Monotonicity. And furthermore, we can use another result by Boris Monotonicity in his book from 2006, that normal cone to the Cartesian sets is the product of the normal cones to each components. So this is a sketch. Of course, the proof is quite long, but here you can see the main points. So, and now we are looking for the subdifferential of the translation invariant functional in the sense of the limiting or basic subdifferential and the singular subdifferential. Yeah, it is possible to show that the structure of the subdifferential of the scalarizing functional here is given in this way, where we have here a hyperplane with lambda equal to 1 from the theorem 11, and with this condition here. And in intersection with the negative normal cone at this point here, where the objective function value of the scalarizing functional is involved and the shifted ZA. And furthermore, it is possible to derive the singular subdifferential of the scalarizing functional from theorem 11 here in this form. Here we have lambda equal to 0. This is this hyperplane H0, where we have here at the right-hand side 0, here we had 1. And then we have this structure for the subdifferential, the singular subdifferential of the scalarizing functional. For our results concerning Lipschitz continuity of the scalarizing functional, we will use this singular subdifferential. This is a main tool, as you can see in the next results. Before we start with these results, I will introduce this property, sequential normal epicompactness of functionals. Here we have an extended real valued function, and this function is sequential normal epicompact SNEC at a point x bar if its epigraph is SNZ at this point here belonging to the epigraph. Yeah, here you can see the relationship between functionals and the epigraph of such functionals. And this will be important for us. Yeah, in the first theorem, we have shown that the subdifferentials of the scalarizing functionals are possible to derive at pairs of the epigraph. And this is essential for the study or for deriving the result that the SNZ property of the shifted ZA and the SNEC property in this sense of the corresponding scalarizing functional are equivalent. We will not suppose that A is solid. However, we need, as already mentioned, this singular subdifferential, and of course, certain qualification conditions. Yeah, here is the first conclusion from theorem 11. Yeah, we can show that the scalarizing functional is SNEC at y bar belonging to the domain of the functional if and only if the shifted ZA in the definition is S and Z at this point here. Yeah, and furthermore, this theorem is important because we can give a characterization of Lipschitz continuity of the scalarizing function without assuming that A is solid and without assuming convexity of A. Yeah, we can show that the functional is locally Lipschitz continuous at this point y bar if and only if the shifted Z is S and Z at this point here, and this condition here is fulfilled, where the hyperplane H0 is given here. So, and in order to prove this, we can use the calculation of the singular subdifferential of the scalarizing functional. This was this characterization or computation of the subdifferential in Corey 12. And furthermore, with Corey 14, we know that under the assumption that A is SNZ, the function is SNEZ. And so we can use this necessary and sufficient condition for Lipschitz continuity of an extended real valued function shown in the book by Boris Modorovich. Here, this is the case if the singular subdifferential is trivial. This is this condition here, and it is SNEZ at the point. Yeah, and this condition implies with theorem, with corollary 14, that we have here the SNEZ property. So, yeah, here you can see that we need a singular subdifferential for deriving the Lipschitz property. So, and a special case, yeah, if C is a non-trivial closed convex and solid cone, the scalarization direction K belongs to the interior of C, and the shifted ZA is this cone Z, then the scalarizing functional is locally Lipschitz. So, and perhaps this result is also of interest because it is related to the translation invariance along the scalarization direction K. Yeah, as a conclusion of theorem 11, we can show that for any y bar belonging to the domain of the scalarizing function and for any t bar, we have this structure for the subdifferential. The subdifferential of the scalarizing function at y bar plus t bar k coincides with the subdifferential of the scalarizing function at y bar. Yeah, this is related to the translation invariance. And also for the singular subdifferential, we have a corresponding result. Here, singular subdifferential of the scalarizing function at this point, y bar plus t bar k, equal to the singular subdifferential at y bar. So these are our results concerning the subdifferential of translation invariant functionals. And we will apply this for deriving necessary optimality conditions in Z optimization. Here we introduce the Z optimization problem with a Z-valued map F in the framework of Asplund spaces. Theta is the domination set defining the solution concept in the next definition, and we suppose that the set of scalarization directions is non-empty. So, and we define the solution concept on the graph of F. This is X bar, Y bar. So, belonging to the graph of F. And we say that this element is a theta minimal solution if this definition is fulfilled. We introduced at the beginning already in one such solution concept. Yeah, as you can see, this is the solution concept based on the vector approach. And of course, in that optimization, one has different solution concepts. The most important concepts are the natural solution concepts by Kuroyeva and many other authors. Yeah, and however, for us, for deriving optimality conditions based on concepts of generalized differentiation, the solution concept based on the vector approach is much more useful. However, it would be very interesting to derive corresponding results for the other solution concepts for that optimization problems. Right. Oh, seems that is not possible. Ah, yeah. Sorry. Yeah. Yeah. And in order to derive the necessary optimality conditions, we need some qualification conditions. Here I recalled two of these qualification conditions: norm convergence qualification condition with respect to the z-valued map F and the feasible z omega, and the mixed qualification condition with respect to the z-valued map F and the domination z theta. We need both of these qualification conditions. Yeah, and if one would check the proof of the necessary optimality conditions, we could see that we could replace this mixed qualification condition by this one here, where the nonlinear scalarizing function is involved. Yeah, so and here you can see the necessary optimality condition for theta millimole solutions of the z-valued optimization problem. Because we are using in the proof the nonlinear scalarizing functional, here you have seen it also in the mixed qualification condition. We suppose that K belongs to the set of scalarization directions with respect to theta, and here we replace in the definition of the scalarizing functional A by theta domination z minus y bar. So, however, this is a tool for the proof. I only would like to mention it here because we can prove the result using these tools. Then, for deriving optimality conditions, we need some closeness conditions. We need PSNC conditions with respect to theta and with respect to the feasible z omega. We need it with respect to the z-valued map F. And then we need furthermore these qualification conditions with respect to F and omega and with respect to F and theta. And furthermore, here with respect to the system domination z, z-valued objective mapping in feasible z. This is the second kind of qualification condition that we need for our assertion. And then we can show here this necessary condition that we get the existence of multipliers y star belonging to the negative limiting normal cone at 0 with respect to the domination z theta, and with this property where the scalarization direction K is involved. And so such that 0 belongs to the limiting subdifferential of the z-valued map F at y bar star plus the normal cone at x bar with respect to the feasible z omega. If you have a look to these conditions, we derive these conditions from the structure of the subdifferential of the scalarizing function phi, where the shifted z is theta minus y bar in the scalarization direction K. Yeah? We derived these properties when we computed the structure of the subdifferential of the scalarizing functional. And these conditions we get from the so-called subdifferential variational principle after the scalarization. Yeah, this is a formulation of Eck-Lang's variation principle using subdifferentials. Yeah, and furthermore, we have to check that all of the assumptions of this subdifferential extremal principle or variational principle are fulfilled. So, and finally, I will give some applications in approximation theory. Yeah, here we suppose Banach spaces. And now, in order to define the vector valued norm, we suppose that theta is a non-trivial closed convex and pointed cone. Yeah, this is an open problem. We supposed here that these assumptions are fulfilled. because in this case it is possible to compute the subdifferential of the vector valued norm. Of course, it would be very interesting to replace this non-trivial closed convex and pointed cone by a more general domination set. Because our applications in section 4 were derived for a general domination set, theta. But here our problem was to compute the subdifferential of the vector valued norm. Using this cone now, theta, we define the vector valued norm by these three properties. And in the case that y is the space of real numbers, then we have here the well-known three properties of a classical norm. Here we can use the structure of the subdifferential of the vector valued norm. These are linear continuous operators with these properties. And again, if y would be the space of real numbers, here you can see the well-known properties of the subdifferential of the norm that we can derive from Hahn-Banach's theorem. These are these properties here. So, and we suppose that the subdifferential of the vector valued norm is non-empty. And then we introduce at first a vector valued approximation problem using a cost function g and the vector valued norms. Omega is a feasible set, ai are linear continuous operators, and vectors ai are given elements. Here we have weights alpha I greater or equals than 0. And then we consider this vector valued objective function where g and the vector valued norm are involved. So here we have additionally such a parameter omega, sorry, this is w belonging to z capital W of x, and this is a control parameter. And furthermore, we understand here the minimization with respect to theta. And we will reformulate this vector optimization problem with a parameter w by a set optimization problem. Here we have a z-valued mapping g of x defined here, depending from x with the parameter w. So, and now it is easy to see that the vector optimization problem is equivalent to this z optimization problem here. So, and then we can derive, using our results, necessary optimality conditions for a theta minimal solution of the z optimization problem. This is x bar, y bar. Here we have some additional assumptions concerning theta because we need some calculus rules for the subdifferential. We have some closeness assumptions concerning the feasible set, and we have some Lipschitz assumptions concerning the z-valued mapping G. Here, this is a PSNC property with respect to the domination set or the cone theta, and this is a qualification condition that this implication holds here. So, and then we get the existence of multipliers with this property here, such that this condition is fulfilled here. As already mentioned, we introduce this very strong assumptions concerning theta because in this case it is possible to compute the subdifferential of the vector valued norm. This is this term here, and the elements Ti are linear continuous operators with these properties. And here you can see again, these properties are related to the structure of the subdifferential of the vector valued norm. This is the application of our results for a very special case. So finally, I would like to give some conclusions to derive necessary optimality conditions in that optimization, where we are using solution concepts based on another approach. So that approach especially would be interesting. And maybe it could be possible to use our results here and further results concerning the relationships between both solution approaches, set approach and vector approach, to derive corresponding results. And another topic for further research would be to compute the subdifferential of scalarizing function related to vector optimization with respect to variable domination structure. Yeah, as already mentioned, in the last part of my talk, I suppose the theta is a cone with certain properties. The reason was the computation of the structure of the subdifferential of the vector valued norm. And here it would be very nice to derive maybe for some other special structures of theta, not cone properties or convexity properties, maybe that theta is star-shaped, to derive the structure of the subdifferential in this more general sense. And furthermore, applications in locational analysis and in optimization under uncertainty would be interesting. Yeah, most of the results of my talk are included in this paper here together with Bao Tuong. Yeah, here are some other papers with Bao about necessary optimality conditions in aspirant spaces. Yeah, furthermore, I would like to mention this paper. This is related also to nonlinear scalarization and a unified characterization of different scalarization techniques, especially by Hiriad Urruti, Zweiter and Drummond, and this is done in this paper with Ramabotsa, Ernest Quintana. Yeah, and here these are other papers related to necessary optimality conditions in Z optimization. Here I may record this structure of the subdifferential of the scalarizing function in special cases. These results were shown together with Mario Storea. Yeah, the main properties of the scalarizing functions are derived here, especially in our book. This was the interesting paper concerning translation invariance. Yeah, for the concepts of generalized differentiation, I would like to mention these old papers by Alex Kruger and Boris Modorovich. Yeah, concerning properties of Z-valued optimization problems and corresponding scalarization. I like to mention our book from 2015. Yeah, this is a paper concerning uncertain optimization. Yeah, the concepts about generalized differentiation are detailed, studied in the book by Boris Modorovich. And this was our earlier paper concerning Lipschitz properties of scalarizing functionals. So that's all. Thank you very much for your attention.
Thank you very much for your very nice talk. So everyone, if you have any question or comments, please just unmute yourself and then ask question, or just write down in the chat or raise your hand. Yeah.
May I ask a question?
You
Sorry,
may,
by the way, I want to start with saying that I share what Joy Deep wrote in the chat. It's good to see you, Christiane, finally after a long break.
Yeah,
sorry, my dog is
nice
trying to intervene. Maybe he has more questions. Thank you for this nice presentation. Indeed, a well-developed theory. And of course, it's good to see familiar things like limiting subdifferentials, normals, co-derivatives, and stuff like that. This is an introductory part. Now I'm coming to my question. So you are, when defining all these concepts, you are mimicking definitions which are introduced normally in the convex setting. But you are not assuming the convexity of this domination set.
Yeah.
You also presented a big list of settings where such definitions work, including economics, Leuenberger, and other things. I suspect that in most cases, in applications, they still assume this domination set to be a convex cone. Do you know examples where such settings actually work without convexity?
Yeah, maybe if you would consider general preference relations in economics, especially the production possibility set could be a non-convex set. These are studies by Leuenberger and others. Yeah, they have not in each case convexity assumptions. And furthermore, in risk theory, coherent risk measures are also related to this nonlinear scalarizing function. And in recent papers, they do not suppose that that A in the definition of the risk measure is convex. They have, especially in the original paper by Arzner and co-authors, they suppose the convexity of the acceptance set. But in the recent literature, they have not these strong assumptions. Yeah, and another example maybe could be in locational analysis. If we would study a vector valued location problem, sometimes it would be necessary to formulate the preference relations of the decision maker by more general domination sets. Yeah, these are three examples from real world problems. And of course, for mathematicians, it is interesting to derive general results. Yeah.
Thank you, Christiane. It's good to see that such applications exist. But the last argument is actually the strongest. It is interesting for us.
Yeah. Yeah.
Sorry, Joydeep. Unmute yourself first. Joydeep, you're mute. Okay.
Christiane, it's wonderful to see you after such a long time, and I'm so happy.
Hello, nice to see you. Yeah.
I want to ask you, because this is the question I am currently facing from referees. You are the top expert in this subject. You can help me. See, the question that comes often is that we develop such rich theory of optimality conditions, which are very mathematically involved and very nice structure, like the one you have given here, which is very interesting. The thing is that they argue that how does these conditions really come to your help when you're computing, even if you put it into a practical setting? Can you help me in this question? How you use these conditions in actual computation, because you are experienced in even computation of vector problems. So how would you use this in computations, these ideas?
Yeah. Yeah, this is a very interesting question, and of course, here I also mentioned it. To develop numerical procedures based on these optimality conditions. However, one has some special problems where it is possible to compute the subdifferential of the scalarizing function or also objective function, and especially the non-convex case. if we would consider a non-convex vector optimization problem, then using this calculus and using the optimality conditions, one has to compute the limiting subdifferential. And this is really a very strong problem. And yeah, we started to do this in locational analysis. There is one paper together with Bao Tuong and Markus Hillmann, a PhD student of mine. And here we computed the limiting subdifferential of the non-convex vector valued function. However, this is really difficult to do it. And it is possible for special structures, and it would be an important point for further research to develop numerical procedures. But I think one should have certain special structures, like for norm terms in the objective functions. Then one could get some useful results. Or if the domination that is starship, such that one can use certain structures without any structure. Of course, then one has only the general optimality conditions, and but this is a very important topic for further research.
Thank you, Christiane. Thank you very much.
So we have a question from Wilfredo. Can you unmute and ask directly to Christiane?
I think now, can you understand me?
Yes, very good.
Yeah, very good. I would like to thank Christiane very much for her clear lecture. It was very interesting. And still a small question to Theorem 20. Are the assumptions for the domination structure in Theorem 20 so strong that the domination, that theta, the domination structure, must be solid, must have inner points?
Yes, this is closely related to such assumptions, especially sufficient assumptions.
Yes.
Or one sufficient assumption that all of these properties are fulfilled is that theta is non-empty. And of course, it would be nice to relax these assumptions. However, the reason is that we need it for the computation of the subdifferential of the vector valued norm. And so it would be a very nice topic for further research to compute the subdifferential of the vector valued norm under weaker assumptions concerning theta.
Thank you very much.
Especially Borwein had derived sufficient conditions for these properties, and they are related to the non-emptiness of the interior of theta.
Yeah, I think so, yes. I think so. Very much, thank you. The best for you.
Thank you.
Thanks.
For you too.
Thanks.
I see one more question from the chat. From Wilfredo Sosa. Can you unmute and ask? Okay, maybe I will read. Okay. But maybe I will raise the question. Differentiability were introduced in order to understand locally behavior at a point and doesn't convexity. Why the scalarization need convexity?
The scalarization doesn't need convexity because here in one of the first results where I record the properties of the scalarizing function, it is convex if and only A is convex, but we didn't suppose the convexity of A. However, in our formal results, we supposed the convexity in order to derive the structure of the subdifferential in the sense of convex analysis. But in our new results, we didn't suppose the convexity of A, and this means that the function is not convex. And this was the reason that we are using the limiting differentiation concept. Yeah, here in the first results that we derived 10 years ago, we supposed convexity, yeah, of the shifted Z, and then the function is convex, and so we have the classical Fenchel subdifferential of convex analysis. And here too, we supposed convexity, but in our recent results, we didn't suppose here convexity. We supposed that the shifted ZA is proper and closed, but no convexity.
Okay, thank you. And any more questions?
I have a question. Is that related to your vector norm? So the value of the vector norm, vector norm is a vector in a cone. So yeah, that's one. There's another terminology, not terminology, notion about vector matrix. It's about it's also about the metric is also a value is a element in a cone. So is there any connection with that? So have you ever heard about that?
Oh, no, however, the intention here was to formulate approximation problem. But maybe this approach that you mentioned could be also used to formulate certain optimization problems. And here one has to check that all of these three assumptions are fulfilled. And with these three properties and the cone properties here, it was possible to derive the structure of the subdifferential.
Yeah, so and then later on you have some result on the qualifications. So, but we don't have like a rational principle for those kind of norm space, and then also we don't have we don't know even what the property of this space we have with that a quick norm like this. Like is that yeah.
Yeah, I think this was included in your PhD thesis, no? And this would be really a very interesting new field of research to study these problems and to derive some assertions. However, it is not clear that one has these properties, yeah? Especially here's the computation of the subdifferential. The proof is dealing with Thorne's lemma, and one needs several very strong tools, and so one has to check that they are applicable in this general case. But it is a very interesting hint to have a look to such problems.
Okay, thank you very much for your answer. So, is there any other questions or comment from the audience?
Juan, maybe I have a question. Yeah. Christiane, thank you for the beautiful
hello,
talk.
Regina. Thank you.
Hello, how are you?
Thank you,
look,
fine.
Very, very nice talk. Look, I wanted to hear, so you have this new concept of the subdifferential, right? Is there also a corresponding concept of epsilon subdifferential as well?
Until now, not. But this would be also interesting. Our intention was to derive the structure of the subdifferential where the shifted z is not convex. Yeah, but yeah, this would be really interesting to consider the epsilon subdifferential and other approaches for such problems, especially, yeah, maybe then it would be possible to compute the structure of the subdifferential or the epsilon subdifferential. Maybe it's easier than in our approach. This is very interesting. Thank you.
Okay, thank you, thank you.
Okay, so if we don't have any more questions from the audience, so thank you very much for coming to the seminar today, and then thanks Regina for your talk. So next week,
Thank you.
yes, we have a speaker from New Zealand. So looking forward to see all of you.
Yeah, thank you very much for your attention and the kind invitation.
Thank
It was
you.
a great pleasure.